Hello, and welcome to 6.1 Circular Motion for the IB Physics SL curriculum. So, like all physics, we need to first define our terms. So, for circular motion, our first term that we're going to define is period, which is represented by a capital T. So, the period is the time to complete one revolution. The inverse of the period is frequency, denoted by a lowercase f, kind of curvy. That way you don't mess it up in your equations. But that's the number of revolutions per unit time, which is typically much more useful whenever we're trying to express how fast something is rotating and moving in a circle. Um, and circular motion is very similar to linear motion in that we have displacement and velocity. So the displacement equivalent is aptly named angular displacement, which is the angle through which an object moves. So if I move halfway through a circle, my displacement will be pi radians. And we use radians because it's a much more it's a much more easily used unit whenever we're trying to actually use the equations. So if we go down to our next bullet, we have angular velocity. So the angular velocity, just like in linear motion, is the derivative of angular displacement. So it's essentially how much of an angle we move through per unit time. So because our angular displacement is in radians, our angular velocity is in radians per second. The angular displacement is represented by theta because, as traditional, that's the angle. Our angular velocity is represented by a lowercase omega. So in order to find the angular velocity, use this equation right here, omega equals 2 pi over t, which makes sense if you think about it. So the total number of radians in a circle is 2 pi. The period itself is the time to complete one revolution. So in the time that it takes to make one revolution, you're moving 2 pi radians. So in order to find the velocity, you just divide 2 pi radians by t, and you get the angular velocity. So moving on, because we're moving in a circle, the speed is constant. So the magnitude of the velocity vector is, but the direction isn't because you're constantly moving in a circle. So at one point you might be going up, down, north of east, whatever. So you can't really attach a certain direction. But what you do know is tangential on its own means the line that will touch another in only one point, and that so happens to be in a circle. The line that's perpendicular to the radius. So tangential velocity is just the velocity of the object perpendicular to the radius. So in order to find the velocity, this is the derivation right here. So the distance traveled, as in linear motion, is just v velocity times your change in t. So your arc length, we know from geometry that it's r times your change in theta. Change in theta will always have to be, your delta theta will always have to be in radians because those are the units required by that certain equation in geometry. So whenever we set them equal to each other, our velocity is equal to your r delta theta over delta t. So whenever we simplify that up, we know that your change in angle over your change in time is equal to your angular velocity. So we can then set our tangential velocity equal to the angular displacement times the radius, which also makes sense because if you really think about it, if two objects are moving at the same angular velocity, meaning they're rotating at the same speed, your object with the larger radius of their circle is going to be moving much faster. This is the explanation for a lot of real world situations such as the Coriolis effect and many other stuff, and it's very useful for engineering. So we have that equation again down here, and then as mentioned before, the velocity is going to be tangential or perpendicular to the radius. So now we move on to force. So the centripetal force is defined as the force needed for an object to maintain a circular path. So if you don't have a centripetal force, what's going to happen is you're just going to keep moving straight, or maybe not in a perfect circle, maybe at a curve. So what the centripetal force does is it's always pointing towards the center of the circular path. So if we move back here, if you imagine it, so your velocity is currently tangential to the circle. If you're moving with your acceleration towards the center of the circle, your velocity vector will then change slightly, and then it'll move in the tangential direction to the circle. So centripetal force will lead us to centripetal acceleration. And the centripetal force, don't try to think of it as its own force. It's not like gravity where it's, I mean, it's always going to occur whenever you're moving in a circle, but it doesn't generate its own force. What I mean by that is centripetal force is just a direction. It's not a force on its own. It's a label applied to the net force on an object as it's moving in a circle. So in IB examples, you'll always see it's typically the tension on a spring or the friction on car tires whenever turning. So just keep in mind centripetal is always just acting towards the center. Centrifugal force is another term that's commonly thought of. Centrifugal force doesn't actually exist because what it is whenever you're turning in a car and you move to the side, it's just inertia. We won't get into that too much, but centripetal and centrifugal just indicate direction, really. But we won't get too much into centrifugal. So in order to maintain a circular path, the centripetal force must also exceed a certain value. What that means is your centripetal force has to be equivalent to this equation down here, F equals mv squared over r, meaning the faster you're going or the faster you're rotating, the greater centripetal force you're going to need. And then, of course, because the greater mass, you would need the greater force. So that's why m's there. So now that we know centripetal force, we can find centripetal acceleration. So using Newton's second law, F equals ma, right? So we know the equation for centripetal force, which is mv squared over r. So because m's in there, we can just isolate our acceleration, which turns out to be v squared over r. And then that second part of the equation right here, the 4 pi squared r over t squared, that's just them substituting in for the omega squared, the angular displacement. So because the centripetal force itself is directed towards the center, your acceleration is always going to be directed towards the center as well. So let's move on to our first example. So friction is the force that turns cars. If you think about it, whenever you're moving in a car, and say you're on a sheet of ice, if you turn your wheels, I mean, because of slight amount of friction, your car might rotate, but your car will have a lot of trouble actually making a turn. So whenever you're turning, the frictional force is what's acting as your centripetal force in this sense, because for our vertical component, which keeps the car on the ground, of course, weight and normal force or reaction force are in balance, and our frictional force is moving us in that circular direction. So if the frictional force, which is represented by mu r, is equivalent to our centripetal force, whenever you're doing an example like this, you would just set them equal to each other, and then you can solve it using the information they give. And as I said before, because the equation for centripetal force is mv squared over r, if your speed is too high, you would need a greater frictional force, which in some cases you might not have, like as in the example of whenever you're driving a car on ice. So for circular motion, on banked surfaces. It's actually kind of weird because if you remember from this example, the frictional force is actually our centripetal force. But in the second example of circular motion, friction is actually working in the direction opposite of our centripetal force. Because on a banked surface, if you weren't moving at all, what would happen is friction, normally because of gravity, because you can divide up the weight vector, as you guys probably remember from whenever we were doing linear motion, there's an acceleration down the ramp due to gravity, meaning you would normally move down the ramp, so our friction vector is actually moving up the ramp. So what you do in this situation is you're going to try to balance out the friction versus the normal reaction force, because if you're moving in a circle, your normal reaction force is actually going to be slightly greater in the horizontal direction than your weight, because of the fact that you're on a slope. So what happens is your normal reaction in this case is going to exceed your friction and act as a centripetal force. The reason we use banked surfaces in the first place, if you guys ever drive on the highway, they're banked because the banked surface will actually help you stay on the right track, and you won't actually have to increase your velocity to such a large amount. It helps regulate speed, and overall you need less friction than on a flat surface, so there's less skidding because of the fact that it's your normal reaction force, the horizontal component of your normal reaction force, that keeps you moving in a circle. So this last example is called the wall of death. You probably won't see this on the IB test, but you might see it in a couple of practice problems. So if you guys ever watch like the like all those daredevils and all the crazy stunts people do, you might see the wall of death, which is essentially just a car on a completely vertical wall, and somehow the car, if it moves fast enough, is able to it's able to stay up on the wall and keep moving in the circle. So what happens is, as you move faster on the wall of death, if you remember, mv squared over r was our equation for the centripetal force. As you increase v, which is actually increasing exponentially because of the v squared, in this case, your normal force is the centripetal force. So therefore, by increasing the centripetal force, you're actually increasing the normal force in this situation because you're completely vertical. So if you recall the equation for friction, it's mu r. So by increasing the normal force, you're increasing the force of friction. So where your car would normally just fall due to gravity, you're increasing the force of friction in the other direction. At some point, your force of friction is going to balance out with gravity, and your direction, or your net force in the vertical direction, is going to be completely negated. You're going to just be moving along the circle in a straight line. And in some cases, what'll actually happen is you just can keep going as far, but that's only if you're able to keep your speed. If people let off of the gas, and sometimes that does happen in the wall of death because people get scared and whatnot. If the car's moving too slow, your normal force decreases because your velocity decreases, and then your friction will be less, and then they fall due to gravity, and then you get all these big accidents, which hence the name wall of death. So yeah, that's the end of 6.1. Thank you and goodbye.